Alright. Hello and welcome back to Geometry. Chapter 6, Section 3. We're looking at medians and altitudes of triangles. Good times. Alright. The median of a triangle. If I take a triangle and split one of its sides in half. Now, one way you can do that is if you're using a compass, you make a little arc from one side, like so, and then from the other side. And then if you connect that arc through the middle, boom, like this, you can find that median, like that. When you connect those medians of each side, you get the median of a triangle. If you connect the vertex to the midpoint of the side, like this, and then the vertex connected to the midpoint of the other side, and then the vertex connected to the midpoint of the opposite side, like so, we get a midpoint like this between those three, and we call that the centroid. So here we have theorem 6.7, the centroid theorem. Now we know these are the midpoints of the sides, so we know that these two parts are congruent. But the interesting fact about the centroid is where these points meet, or the point of concurrency, is 2/3 the distance from one side, from the vertex to that midpoint. So from B to P is 2/3 the distance from all the way from B to F, or from P to F is 1/3 the distance all the way from the vertex to the midpoint. Okay, using this, here's an example. We know the distance from S to the centroid. Important that we know this fact. Centroid. That means that 8 is 2/3 the distance from S to W. 2/3 SW. So now we see, what are they looking for? They want to know SQ. We know SQ is 8. We want to find QW. So we want to find this distance, and we want to find SW. Well, we can find SW with this right here. To get rid of that fraction, we're going to use the reciprocal, multiply by 3/2. So multiply this by 3/2. 3's cancel out, 2's cancel out. 3 times, we can simplify 8 and 2 here. We get 4. 3 times 4 is 12. So we know that the entire length SW is 12. That's this one checked off. We could find 1/3. We know that QW is 1/3 of this. Or we could say, well, this is 2/3, so half of that is 1/3. So we could say half of 8 is 4. So this has to be 4. Or we could do 1/3 of SW equals QW. So 1/3 of 12 is QW, which is 4. Moving right along, finding the centroid of a triangle. We're given the coordinates of triangle RST with the vertices R, 2 and 1, S, 5 and 8, and T, 8 and 3. Now, first thing I always recommend doing if you're just given the coordinates is graph this so you can get a visual of that. So if we graph that, we can see this is what it looks like. We want to find the coordinates of the centroid. So we would want to take one of the sides and find the midpoint of a side. So the concept here is find the midpoint of a side, so like this one for example, and then find 2/3 the distance from the vertex to that point. Okay, so here in this illustration we've already found that, but we're going to go ahead and find that. Now, the easiest one to work with is if you have a vertical or a horizontal one. Okay, and you can see here this midpoint is going to be halfway in between at 5 and 2, and that gives us a vertical line, so that's very nice to work with. Alright, so we'll find the midpoint of R and T. We'll use a midpoint formula for that, so that's 2 plus 8 divided by 2, and 1 plus 3 divided by 2. And that's how we come up with 5 and 2. So that's the midpoint between these two lines. Okay, now we want to find 2/3 the distance from 5,8 to 5,2. Now it's convenient when it's a vertical line like this because the distance between these two is just 8 minus 2 because there's no difference between the x values. So 8 minus 2 gives me a distance of 6, and so I'll take 2/3. 2/3 times 6, so 6 times 2 is 12, divided by 3 is 4. So the distance from these two is 4. All I have to do is subtract 4 from this point right here. Okay, so I would do 8 minus 4, 8 minus 4, and that would give me 4 for the y-coordinate. Since this is on a vertical line, the x-coordinate stays the same, so that point is 5 and 4. I could generalize what I just did here, saying I'm going to have to subtract 2/3 from the original y-coordinate. So I could take the original y-coordinate minus, this was 2/3 of the distance, so 2/3 of the distance from this y-coordinate to this y-coordinate, 8 minus 2. And all of that would have been one expression. What I just did, 8 minus 4, well, this comes out to be 4. How's that 4? Because 2/3 times 6. How's this 6? Because 8 minus 2. Okay, so this would be how I would find that coordinate. I only did that for the y-coordinate. So this was the vertex. I would call that y of, if I generalized it, I call it v for the vertex, but for some reason they used v down here. So for this example, I use ys minus 2/3 ys minus the y value of that point v. So I would generalize this probably further down to y of the vertex minus 2/3 y of the vertex minus y of the midpoint of the opposite side. So there's a general formula. And if it's not a vertical line like we had here, you'll have to do that for both the x and the y value. All right, moving right along. The altitude of a triangle is, we can use altitude pretty much interchangeable with height. The altitude is in a right angle on the opposite side. Now, notice that sometimes if you have an obtuse angle here, that altitude is going to be outside of the triangle, but it is still in a right angle on an extension from that side. Now, if we take the altitude from each side, so I go from this vertex and do the altitude, so in a right angle on this side, I go to vertex A, take the altitude, right angle, where all the three altitudes intersect, that there's one point, the point of concurrency is called the orthocenter. Okay, those lines are altitudes where they intersect. The point of concurrency is the orthocenter. Now, here are three different examples. Depending on the type of triangle, the orthocenter is either inside the triangle, or it is on the triangle if it's a right triangle, or if it's an obtuse triangle, it's outside of the triangle. Finding the orthocenter of a triangle. Okay, we will have to work with perpendicular slopes here. Again, we're given vertices here. I recommend that you graph it. So I've set up a graph. We're going to graph those sides. There we go. Now, there we go. I want to find the orthocenter. That means I need at least two lines, two altitudes. In this case, notice I have a horizontal line, so finding the altitude is pretty easy here. That's going to be this line. I'll start with that. Okay, that is a vertical line, so it's going to be x equals, so that line is x equals, and that is -2, so x equals -2. All right, now I want to find another line, either from here, the altitude from Z onto XY, or from X, the altitude onto YZ. I'll go from X to YZ. So I'm looking for this line here. That comes in a right angle on this side. So to try to figure that out, we know that slopes of perpendicular lines are opposite reciprocals. So I'm going to find the slope of YZ first. The slope of YZ is, we have -2 and 4, and 3 and 1, -1. That's points Y and Z. The slope here is from 4 to -1 is -5. From -2 to +3 is 5. So that slope is -1. So a perpendicular slope to that would be 1. So the slope of this line right here is 1. That means I didn't graph that quite correctly. I have to go like this. Okay, that means up 1 over 1 from there. Now I want to find the equation of this line that goes through this point, x, with a slope of 1. So it goes through -5, y equals mx plus b. Fill in what I know for x and y, -5 and 1, and then solve. So -1 is equal to -5 plus b. Add 5 to each side, and I get 4 is equal to b. Okay, so it's going to cross right there. So y equals 1x, or x, plus 4 is the equation of this line. Now I have to set them both equal. Okay, and this one says x equals -2. So I can plug in -2 right into here. Say, when is this line going to be at -2? When y equals -2 plus 4. And that is when y equals 2. So that point where they intersect is when x is -2 and y is 2 right there. And here is a quick summary of all the things that we've done in Chapter 6 so far. Perpendicular bisectors. We know they come down at a right angle and bisect the other side. Angle bisectors bisect the angle. We have the point of concurrency is the incenter, same distance from each side, whereas the circumcenter is the same distance from each vertex. The median we just looked at today. We know that it splits each of these sides into 3 parts. We have 2/3 from the vertex and then 1/3 to the side. And the altitude, where the altitudes meet, is called the orthocenter. There we go. Talking about triangles today. Lots of fun. All right. See you in the next lesson.